Welcome to session number 10 in the series Analog Circuit Design using ADS. I'm Anurag Nigam, and in last section I discussed a cascade amplifier, and we have been discussing a lot of single-ended amplifiers. Now these single-ended amplifiers suffer from one common problem. That problem has been the bias point. If you establish a bias point and a gain is very high due to aging and temperature variations in VT, the bias point can slip out of the maximum gain region, so the input voltage range is very small. Now this has to be addressed, and the simplest way to address this is a differential amplifier, which I'm going to discuss in this session, and then following it I would be discussing an OpAmp. Okay, so now what is the reason for small input voltage range is that the DC is somehow coupled with the AC stuff, right? Okay, so this has to be decoupled, right? So now the basic configuration goes like this, that you have a PMOS which provides in a current, right? So this is diode connected, right? So this is going to force certain current into the differential stage. And what is the differential stage? I'll just draw it out. Okay, so you have a PMOS stage which has a differential configuration like this, and then it has a current mirror load. So that current mirror load I'm going to draw here. Okay, so that's a current mirror load. Sorry. Okay, so that's a current mirror load. Now the gain stage in this case is this transistor, not this transistor. This is not a gain stage, and I'll tell you why this transistor is there. Of course, the reason this doesn't contribute to a gain is because this is a diode connected transistor. So if this is a diode connected transistor, then its impedance is 1 over GM. So the gain of this stage will be GM-RO, right? And RO is 1 over GM. So the gain would be 1, right? Okay, so that is what is going to happen, right? So this will not be a gain stage, but still it is required. I'll tell you why. Okay, so just focus on how it works. So let's say if I have a signal VP, and let's say there is a signal VM. Let's say what happens to VP. Now let us assume that this VP and VM are at DC values. So this is V overdrive, and this is going to be V overdrive plus VT, and this is also V overdrive plus VT. Okay, so now if these two transistors, which is, let's say this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So let's say transistor number 3 is matched to transistor number 4, so they are same in size, right? So when that happens, then V overdrive plus VT for both are same, right? So that means that the net, if this voltage is at VP is held at twice of V overdrive plus VT, and this also is held at twice of V overdrive plus VT, okay, or more, right? So they are held at same DC voltages. Then you have a AC on top of it. So now this transistor number 3, so if you put in a VP signal, then VP at the common, let's say this is a fixed voltage, right? Because this is a fixed DC voltage, so you can assume this to be a small signal ground. So this is small signal ground. The voltage here would still be VP, because this transistor number 3 is a source follower. So the gain, so basically the output VP dash, for example, VP dash would be equal to GM3 plus GMB3. It's a source follower, plus GMB3 plus GDS3, right? Plus GDS3 plus GM3 GMB3 GM3 GMB3 plus GDS3 plus GDS2. Okay, so now let's assume that this value is much greater than this value. Then this gain would be approximately 1. So we would have VP dash would be equal to VP, because the gain is 1, right? Now transistor number 4 is like a common what you call a common gate configuration for VP. Okay, so VP is applied to the source. So VP is applied to the source here, and that basically appears at the output, right? So VP is applied at the source, right? So now the gain would be, so the output voltage because of VP would be VO, okay, 1, shift F4. Okay, so now VO1 because of VP would be equal to G, the gain times, so this transistor 4 is a common gate for VP now. Okay, so the output voltage because of VP is VO1, and that would be given by the gain of this stage, which will be GM4 divided by, sorry, GM4 divided by GDS6 plus GDS4, okay, times of VP. So this will be the output voltage because of VP. And let's say what is the output voltage because of VM. So this is going to be a common source. So transistor 4 would be a common source for VM, because the source is at the source of this transistor 4 is at a small signal ground, right? So it will be a common source. The gain of this would be minus GM4 divided by GDS6 plus GDS4 VM. So by superposition, if I was to add VO1 plus VO2, that will be output VO, which will be equal to, and which will be equal to GM4 minus GM4, right? Let's see. Okay, so don't worry about this. I'll clear that. So it will be minus GM4 by GDS4 plus GDS6. So this I take common, VM minus VP. VM minus VP. Is that correct? Or you can just say, you can take the sign in VP minus VM. So now that means that for if P was to go high and M was to go low, right? So this node will go high. The output node VO will go high. That means this is a non-inverting terminal, and this is going to be an inverting terminal. Okay, but now what I have done is, okay, so that's what this expression says, that for signal VP the output voltage is going to have a positive gain, right? And for signal VM the output voltage is going to have a negative gain. So that's why I'm saying that that VP is a non-inverting terminal while VM is a inverting terminal. Now the way I label that, okay, is going to change if I introduce another stage over here. Now what's the problem with this differential amplifier? The problem with this differential amplifier is the following. Now it is responding to the difference of the signal. That's why I'm calling it differential amplifier, right? So I can write minus GM4 by GDS4 plus GDS6 times of V diff. Okay, so this is going to be a differential gain. Okay, so differential gain of this differential amplifier. Now there is an issue with this. Okay, so the advantage we have already seen. The advantage is if we keep the DC voltages of VP and VM to be same, that means that if they track together, then there is a very large input voltage range, and that large input voltage range will go from VDD minus twice of V overdrive plus VT to VDD minus twice of V overdrive minus VT to some on the lower side it is going to be V overdrive here and V overdrive here, twice of V overdrive, okay, plus VT twice of V overdrive minus V overdrive minus VT, V overdrive twice of V overdrive Okay, so basically the range would be something like this, that it will be for this amplifier VDD minus VO twice of V overdrive minus VT. That is going to be the higher value of voltage, and the lower value of voltage is going to be we are going to have overdrive here and we are overdrive here. So this node is going to be twice of V overdrive, and then you have to go minus V overdrive minus VT. So of course you want that to be in threshold, so the voltage here can be V overdrive plus VT. So the output voltage is going to be V overdrive plus VT. Okay, so this is my swing for the output voltage, right, on a differential stage. Now what about the input voltage range, common mode? So the DC voltage is now a common mode. So what do you mean by common mode? It means that if the voltage to VPs with the voltage to transistor 3 and the bias to transistor 4, they are tracking together, right? They are equal, they're tracking together. Then there is a large range, input voltage range, right? Okay, so what I was explaining you is, okay, so let me go back to my range. Okay, so I was saying is that as long as the DC voltage for transistor, sorry, let's go to the differential stage. As long as the DC voltage for transistor 3 and transistor 4 or the bias voltage are the same, okay, as long as they are same, then they have a very large input common mode voltage range, and this is the large input common mode voltage range, VCM. Okay, so that means that we have got rid of that problem. That problem is due to the high gain input voltage range is small. But here you can have the small signal gain to be large, but the common mode input voltage range can also be large. So that's the whole point here. Okay. As far as the differential gain goes, differential gain is the same as that of a common gate or a common source, which is minus GM4, GDS4, GDS plus GDS6, right? So this is the differential gain AVD. Now, okay, so now another point to note here. This amplifier has a problem. The problem being that VO has to be held at the same voltage as the voltage across here. Okay, so if this voltage is same as this voltage, then these two currents, for zero differential in, these two currents would be equal to I tail, which is I tail is here, divided by 2. So each branch is going to have I tail by 2. Okay. Now, if this voltage VO, DC voltage where it is held, is different, then there is going to be what is called systemic offset. So that means that the common voltages have to be adjusted with respect to each other. So what you give DC voltage to VP and DC voltage to VM, that has to be adjusted to account for the difference in this current, drain current. Okay, so that is called systemic offset voltage. Now this can also be overcome if I was to put here a transistor which has the same overdrive as 5 and 6, right? So this results in what is called an OpAmp. So OpAmp basically is same as a differential amplifier, but it gets rid of the systemic offset voltage. So let's see what an OpAmp will look like. Okay, so as usual, you are going to have this stage which is a current mirror, and let's say this is a 1:10 current mirror, and then I'm going to extend this into another current mirror over here. Okay, that is also 1:10. So this is also 1:10, right? So these two transistors are same. So this is 1 and 2, and then this is diode connected. This is my reference current, right, IREF, and then I tail is 10 times, so this is 10 times of IRF. Okay, now let's assume that this is my gain. These are my two gain stages, right? So these are my two gain stages. Okay, now these two gain stages have a current mirror load. So basically this is 5, this is 6. 5 doesn't give any gain because 5 is like a for a VP signal, which is VP over here, this is like a common drain. For VM signal, this is like a common source, and this transistor 6 is a common gate for VP signal, right? So now if I take this portion and over here I add a transistor, so I have this as 1 2 3 4, sorry, let me do the numbering again. So this is 3 and 4, transistor number 3, transistor number 4, this is 5, this is 6, this is 7, this is 8. Now transistor number 8 is another gain stage which is going to be following this differential stage, but the overdrive voltage of transistor number 8 is going to be same as the overdrive voltage transistor 5. So V overdrive plus VT over here would be same as V overdrive plus VT over here. So then these two nodes are going to be held at same DC voltage, right? And this will assure that I tail on both sides are going to be balanced, and that will get rid of the systemic offset voltage. Now if you know that if this current is 10 IRF, this current is also 10 IRF, because transistor number 2 is identical to transistor 7. So IRF flows, 10 times of IRF is flowing. So if this is twice the current, then this size of this transistor to be same overdrive. Okay, so how do you say? Okay, so the overdrive voltage of this transistor should be the same as this one. Okay, so let's say what is the overdrive voltage? V overdrive 5. V overdrive 5 is equal to I tail by 2 into 2, okay, divided by GM. Or we write a different formula for that. Wait, let's write a different formula for that. Okay. Okay, V overdrive 5 will be equal to twice of I tail by 2 square root of mu n cox w by L5. Okay, and in this case should be equal to V overdrive 8, which will be equal to twice of I tail. Okay, yeah, twice of I tail divided by mu n cox w by L8. So now if this is so, then w by L 5 twice of that should be equal to w by L8. So this will get rid of the systemic offset voltage, and then you will have an output voltage here. So now what is the gain of this stage? Okay, so the gain of the differential amplifier, okay, is GM4 times of divided by GDS 4 plus GDS 6. So this is the gain of this stage, and then there, if I was to do a minus sign here, right, then it will be, so if I do a plus sign, it will be VP minus VM, right? So if I do a plus sign, it is for VP minus VM. Okay, just 1 second. That is the differential input. Now the additional gain which will come here will be because of transistor 8 as a common source. So its gain would be GM8 divided by GDS7 plus GDS8. GDS8, right? Okay, times of this, okay, and it will be negative number, should be equal to a V differential. So this will be the differential gain of an op amp. Now if I want to keep if I want to keep VP and VM same, and so this is a 180-degree out of phase, right? So what will happen is, if VP goes up and VM goes down, then this node goes up and then this node goes down. So that means that if VP goes up, this node goes down. Then what will happen is that this side would be the inverting terminal and this side would be the non-inverting terminal. Let's think it this way. If this inverting terminal goes up, non-inverting goes down, then this voltage is pulled up. That means that VO is pulled down. So this is the inverting terminal and that's the non. Now if non-inverting terminal goes up, then this node is going down. So when this node is going down, this is going up. So this is correct. So left hand side is the inverting terminal, right hand side is the non-inverting terminal, right? So this is all we have to understand for our OpAmp. Now the next thing comes is op-amp compensation. So we are going to discuss that op-amp compensation later on, but let's put this together in the design form. So I'm going to go here and say new schematic, and I'm going to say here TWO two-stage op-amp. Okay, I'll create the schematic. Okay, and then I am going to create a differential pair. So let me just go to a single-ended amplifier, for example. Common gate would do, right? Okay, so in this case I am going to copy the current mirror. So this current mirror I'm going to copy along with this, and maybe this transistor for the load. Okay, Control C, and then I'm going to just paste it over here, Control V. Okay, so now this I keep aside. Now I am going to have this 1:20, right? Now if I have half the tail current, so if I want to keep this overdrive same, then I should halve it, but I don't have it. Really, I don't. Or I can halve it if you want. Just let me flip it out. F5. Has to move the text here. Let me make sure I'm recording. Yes, I'm recording. Okay, so now I'm going to do this connection. Okay, this is done. Now the NMOS devices are going to be half of that, roughly, because the mobility is actually 1/3. So this is going to be, let's say, 10. Okay, and I'm going to just repeat that on the other side. So I'm going to just combine it, or maybe I'll do it later on when I make a symbol for this. Okay, so now I take this transistor, right, and I'm just going to copy this over here. So this is going to be same size. Okay, this is the same size. Okay, so now it is going to be twice the size here, for the overdrive to be same. So that's why I'm supposed to halve this. So this was 10, this is 10, then this is going to be 5 into 2.5, that will be 12.5. okay, so that doesn't match. So how about I do the following, I do this as 4 and this is 40. okay, so this is still 1:10, and this one remains 20, and this one remains 20, and this one remains 10 and 10, half of that, and then the other transistor is going to be twice of that for systemic offset voltage. So this is going to be twice, so this is going to be 20. okay, so now having done that, let's see how does this scale. okay, so this is going to be still half of that, so that's okay. So the output voltage range is going to be okay here. okay, so now this is being done, this is my output voltage, and I can drive capacitive loads with this. I cannot drive resistive loads because I cannot draw a lot of current out of this. So for now let us test this. okay, so to test this, this is my non-inverting amplifier side and this is my inverting side. So I'm going to take sources frequency domain and directly do a AC here, because I have very large common mode range, so really it doesn't matter what is my DC voltage. I'm going to set this to 1.2 volts. okay, because it will be well within the common mode voltage range. okay, and this time I'm going to give 0.5 from this side, and 180 degree out of phase I'm going to give 0.5 from the other side, so that the total differential input is going to be 1 volt. right, so I'm just going to copy this one over here, and this is going to be 180 degree out of phase, 180. okay, okay, so now this is my differential 1 volt input and this is my output VO. So I'm going to label this as VO. okay, one good practice is to make this VCM. VCM means common mode voltage, so I'll declare a variable VCM. okay, and VCM I'm going to declare as a variable VCM, and to start with I'm going to keep this as 1.2, but this common mode voltage range is very large, as we will see. okay, VCM is 1.2. now I am not putting any capacitive load, I'm just going to plot V overdrive, right? So all I need is a AC simulation AC. okay, and in this case I'm going to go from 1 Hertz logarithmic to 10 gigahertz, and I'm going to do 80 points per decade, or sorry, 80 points per decade, and in the display I'm going to just put this as that. okay, so I'm doing 80 points per decade here. Now with this set I can just hit here simulate, isn't it? Anything else? Everything looks okay to me. okay, so I am going to hit simulate. okay, and I'm going to plot VO, that will be the gain, differential gain. okay, and it's too poor. Just 1 second. X-axis is log, so I only have a 30 dB gain here, 25, which is wrong. Let's see what has happened here. 0.5, 0.5, 180, VO. This is 4, this is 40. So the way to increase current would be if I lower this to, let's say, 20. So then all the overdrives will go down, it doesn't matter. Then this will be 200. So let's simulate that. Okay, 30 dB gain. What's happening over here? Oh, that's the reason. This should be 40. That's the problem. Okay, now it's correct. Marker new. So this is the gain, differential mode gain. Right? So the gain is around 60 dB. Let's look at the phase. Okay, so here the phase wraps. So I will put here something called unwrap. Unwrap the phase. Okay, so this is the roll off, right? Okay, so my gain rolls off here, so I'm starting with 0 and I don't have a margin here. That means I have to do frequency compensation. Okay, so for that I'm going to just do a blindly some compensation here, which later we are going to derive it. So for now, let's say this is roughly equal to, let's say, 450 ohm, as we have figured out earlier, and this is going to be equal to 1 picofarad. Okay, no, wrong. That's fine. And then what I'm going to do is I'm going to hit a tune and I'm going to adjust this lead compensation here. Look at what happened over here. So if I was to put a marker here, okay, so let's see what is the margin. Okay, here. So at this point 92 degrees is the phase margin, right? Because I started with 180, right? 92 degrees is the phase margin and the gain is around 61 dB, right? And let's see the first corner frequency. The first corner frequency is going to be at 61.6, 60.6, 59.6, 58.6, 58.6, sorry, 58.6, 58.6, roughly 99 kilohertz. Let's see if I'm recording. Yes, 99 kilohertz. That is even smaller than what happened with the cascode, right? Now let's see if I can improve the corner frequency without sacrificing a lot of gain, right? So let's go to the tune here and see the corner doesn't move much, right? With this the corner is going to move, right? So the corner has moved 59.6. okay, so up to 270 kilohertz, and let's see what happened to the margin. So we have to find the zero crossing is over here. It's still 100 degree margin. Okay, so let's see this capacitor can be reduced further. So I want to see how much can I improve. Okay, so now let's look at the margin. Oh, one mistake I'm doing. I'm rolling from 0, right? So then here it will be 180 minus 114 or 115. Okay, 180 minus 1 is 65 degrees margin here, right? So that's the question. It's a 65 degrees margin here. So I cannot sacrifice. I want something like a 80-degree margin. So it should be around 100 at the crossover. 110. Okay, so that's a 70-degree margin. Okay, so let me just check this one. 108. Yeah, crossover here 530 megahertz. 94 degrees means I have got 85-degree margin, 86-degree margin here. Let's look at the corner frequency. Corner frequency is 250 kilohertz. Okay, so this OpAmp is usable up to 250 kilohertz with a gain of 60 dB, right? 61 dB. And then it has a phase margin of 180 minus 94. Okay, so that's 86 degrees of phase margin it has. So this is an example of a OpAmp design. So I'm just going to update. So just one second. Just going to update this and close this. Okay, so I'm done with the compensation part. Okay, and I have a result which looks like over here. Okay, I have a 86 margin, 61 dB gain, and corner frequency 250 kilohertz. So this can be used up to 250 kilohertz. So this is a OpAmp design example, and I am going to stop here. In the next session, it will be a little more theoretical, where I'll cover frequency response, high frequency response of all the amplifiers up to OpAmp, and that should wrap up the fundamentals of analog circuit design. But then I will proceed to more advanced topics from here, right? Great, thanks a lot. Thank you.